I have already given you a brief introduction about P and I controllers. Few more controllers I want to discuss here in the next few slides. Okay, what you can see in this slide, this is a mathematical representation of two action, proportional, you have seen this, and the second part is the derivative controller. So if you look at this part solely, the relationship between U and E is represented by derivative action here. This is why we call it as a derivative controller. But due to a certain reason that I will discuss with you later, derivative action will never run alone. It always be combined with proportional controller. That's why I put it in this equation. The controller is a combination of P and D actions. You can transform this equation into Laplace domain like this. So this is another representation of the transfer function of a PD controller in Laplace domain. So this PD controller, a combination of proportional and derivative action in our controller here, there are two parameters on it, Kp and Td. Td is what we normally refer to as a derivative time, and Kp basically is just a proportional gain there. In some literature, derivative controller is sometimes also called as a rate controller. And magnitude of controller output, in this case, of course, is proportional to the rate of change of the error. The controller output because of the D action is proportional to the first derivative of the error. That's what is represented in the mathematical equation in the previous slide. So in the previous slides, we have already discussed the advantage of using P, the advantage of using I. I mentioned to you last time, you use P if you want to improve the transient performance, if you want to make your system response faster. You use I if you want to improve the steady state performance, the accuracy of your system even further. But then why do we use D? We use D to improve further the stability. What do I mean by stability? If you want to stabilize your system, D is the best choice. PD, of course, because as I mentioned, D will never stand alone. So you use PD if you want to stabilize a system, or if you want to increase the damping in your response, you also use PD. If, let's say, you have a system, the system is oscillating too much because the damping is too low, you want to minimize the oscillation in the response, you can use this PD controller. So in general then, PD controller, normally we use it to minimize the oscillation in our response. It tends also to amplify high frequency signals. If you have input that contains high frequency signals there, it will be amplified in your response. So PD control is not really suitable for the application with high frequency input. In addition, as I mentioned, D normally we combine it with P, but you can also combine it with PI. In such, we will have a PID controller. Okay, so what is PID? Intuitively, of course, PID is a combination of P, I, and D action. Why do you need PID? We use PID to combine all of the advantages of P, I, and D. P to improve the transient performance to make the response faster, I to minimize the steady state error or to improve the accuracy, and D to minimize the oscillation in your output. So of course in mathematical form you just combine all of these and then you will get this relationship. Just one few remarks, very short remarks on the PID controller. PID controller is pretty common in industrial application. Sometimes they use it to maintain temperature, pressure, level of a constant value of any possible value, and also to minimize the effect of disturbance in many engineering plants in industry. There are many ways to design a PID controller. You will learn later on the second part on how to design PID controller in more systematic way. But in industry, there are also an established procedure to design this PID controller from more in a practical way by using a method that is referred to as Ziegler-Nichols method. So to summarize what we have already discussed in this introduction of this controller design, just few points here that I want to highlight. In particular, we only discuss proportional, integral, and derivative action in the controller. But actually, there are many more than that. But these are the most important things, I think. So just to highlight a few points here, proportional controller, we use it normally to improve the speed of your system, to make your system response faster. And you can use it also to minimize the effect of disturbance. Integral action, normally we use it to improve the accuracy, to minimize the steady state error. But using this integral action might result to an oscillatory response, and you don't like it, of course. And then to mitigate this oscillation, we introduce derivative action. So basically, derivative action will add more damping technically to the system. Then the higher the damping, the less the oscillation in your response. Or in other words, then I can say derivative action will increase the stability of the system. So in practice then, if you want to achieve all of these three objectives, you just combine all of them. You use PID controller. Derivative action, I want to add one more thing here. Derivative action will allow us to use a larger proportional gain. So by introducing derivative action, the limit of stability in your system to the proportional gain will increase. So in one sense, derivative action will also add more stability to your system, giving you more freedom to increase the proportional gain in your controller. As a summary of what we have already discussed, so we have discussed on different types of controllers. So this concludes all of the topics in this part of a dynamic system for control theory course. Okay, thank you for your attention.